gentlemen, I'm happy to be here and invite all speakers to Zoom session after the first scientific session of the second day. And now I'm opening B2 session, and the first presentation will be reported by one of the co-author of the paper entitled "Lightweight Deep Neural Networks for Dense Crowd Counting Estimation." So please, you have a floor now. I guess it will be Stanislav. Yes?
Yes, I am. Thanks, Alexei, for the introduction. So I guess I can start now.
Yeah, please.
Let me demonstrate my screen then. The topic of our paper is lightweight deep neural networks for dense crowd counting estimation. My colleague Aliaksandr Leunikau and I prepared it. So crowd surveillance is an extremely important task in rather many activities, such as industry, traffic organization, security systems, and so on. There are such different tasks to complete in this activity, such as crowd detection, estimation of some crowd characteristics like density, size, etc. The most of these tasks are successfully completed mainly by artificial neural networks. There are several different implementations of them, but in our opinion, the main con of these models is their difficulty. It takes too many times sometimes to train them and basically to use them. So in our paper, we addressed the task to build a lightweight neural network which can count people on still crowd images with decent accuracy and spending not too many time. And to accomplish this task, we have set such goals, which are represented on this slide. So basically, we considered already existing models, and then we tried to simplify them. For our task, we decided to use CSRNet, which stands for Congested Scene Recognition Network, and designated by these authors. The architecture of this network is represented on this slide, this one. Basically, it consists of two parts. One part is these layers, which are legacy layers from well-known VGG16 network. there are convolutional layers, which are denoted by conv. 64 stands for kernel size. MP is max pooling layer, which have a size 2 by 2, and other layers are using dilated kernels with corresponding sizes 512 to 156, etc. We developed two shallow networks. They have these architectures. They also have legacy layers from VGG16 network and networks with dilated kernels. Both shallow networks was trained on the Shanghai Tech dataset, which consists of part A and part B. These datasets consist of still images with dense crowds on them. On this table, people counting on these crowds are shown. So in part A, we have captures with more dense crowds than in part B. For each image, we have ground truth. From the ground truth file, such a density map can be built. We built density maps for every single crowd image. The example is shown on this slide. And Shanghai Tech dataset can be referenced. The reference to Shanghai dataset is represented on the slide. It's not our dataset. It have already been built. So we train our datasets by using a validating dataset, which consisted of 20% of random 20% of a trained dataset. We use this loss function. It is mean squared error. By an eth with hat, we denoted an estimation for ith image. An ith is the ground truth for ith image, and n capital is the size of trained sample. And we use such accuracy metrics as mean average error and mean average percentage error, and absolute and relative characteristics respectively. On this slide, we can see results for both part A and part B as trained data sets. On the horizontal axis, number of epoch is shown, and on the vertical one, mean average error is represented. As one can conclude from, for example, from this chart, the first shallow network demonstrated rather good results, which are comparable with the original network. On the contrary, for the second shallow network, we have not so good results. At first, because they are unstable. We have peaks here, for example, here, and because of the lack of accuracy. For part B, there was less epochs. That's why represented results can be considered as the worst ones, but for the first shallow network, we have also results which are comparable with the original network, though there are such instability here. And there is a table with results on training time and MAE and MAPE metrics results. From this table, it's clear then both shallow networks takes much less time than CSRNet to do our task. And let's see on MAPE results. For them, we have errors like 25%, 30% when training on part A dataset, and about 20% when training on the dataset B. So we can conclude that for B dataset, we have obtained decent results, both in terms of time and accuracy. And there are conclusions of my report. Please feel free to ask your questions.
Okay. So thank you, Stanislav, for your presentation. It was nice, and I would like to say that, good work for your future results, for your future work. Well, I see no questions in chat, and the same in YouTube. Probably as we need to be in schedule, you can write and type your questions just in the channels, in Telegram channel, in YouTube chat, or just in Zoom, among other speakers. So we will proceed with the next presentation towards creation of
thanks for attention.
Okay. Yeah, just close your screen because we need this for the other speakers also.
Okay.
Yes, thank you. So again, the next presentation will be given by Boris Assanovich, I guess. It is entitled Towards Creation of SmileID Obtained for Face Biometric Blinded for Concantenated Corrected Codes. So you have a floor, please, Professor.
Thank you. Do you hear me?
Yes.
Okay, just a moment. So it's nice to hear everybody here, and thanks organizing committee for the opportunity to make a presentation today, and also thanks for comments, and you're welcome to ask questions. I will present the work. The title is Towards Creation of SmileID obtained from face biometrics binded to concatenated error correcting codes. The work was done at Grodno State University. And the outline includes Smile definition of concept of SmileID, our goal and previous works, autoencoder structure, features and their separation, biometric parameters, biometric identification, verification, biometric encryption, and fuzzy commitment scheme, RAS code and biometric noise, temporal smile characteristic, structure, calculation of code parameters, experiments performed with SIA, feature space deformation symbols, evaluation of FRR, key size of concatenated error correcting codes, and conclusions. So the smile is founded by flexing the muscles at the sides of the mouth, and some smiles include a contraction of the muscles at the corner of the eyes. A smile is one of the basic emotional states, shows that you are friendly, relaxed, open, and happy. A human smile that is a key factor in determining person's psychological state can implement the concept of SmileID. We know Face ID, that is a facial recognition system developed by Apple in Cambridge for iPad, and the system allows biometric authentication by the use of infrared picture. We also know Video ID, the video record on a mobile phone of PC camera for web money applications. And also we know SmileID, that is a digital authentication service that uses biometrical facial recognition for access control. There are several addresses below. Our goal in previous works, the main goal to construct a new biometric crypto system based on smile imprint from video frames with the use of autoencoder and fuzzy commitment scheme. Miratkarian et al. Applied dynamic face features extracted from videos. The statistical properties of facial distances were studied by DBClub et al., who developed UVA-NEMO smile database. In our lab, we constructed a system 1 based on Hawk structures. However, it was not very good performance of this system, and we decided to develop new one. Recently, the face deep features and creation of a smile face imprint was done. We use autoencoder that performs a nonlinear transformation of feature space and consists of two parts, encoder and decoder. Encoder translates input to Z, this is a latent layer, and then decoder restores this signal from the code. The goal of the encoder is to learn the representation for dataset and dimensional reduction. We apply the staked autoencoder that has two hidden layers trained and by unsupervised algorithm and then fine-tuned by a supervised method. We used features of autoencoder with the help of transfer function. And here we see the superscript that represents the I+1 layer. And vector X prime has a vector from real numbers that is a weight matrix and is used to get features. Efficiency depends on similarity rates determined by root mean square distances. Separation of the classified classes can be defined by decidability index, where parameters are genuine and impose a mean and various distributions here. And we know that biometrics is very often used for different applications today, and we see here a lot of modalities. However, we have chosen the face because the distance is quite good from 1 to 3 meters, and it's very easy to get the ID of the person. And we know that biometric parameters normally characterized by several parameters as false acceptance rate, FAR, false rejection rate, FRR, and also equal error rate. And we also measure the receiver operating characteristic of the system. We can speak about the biometric identification or verification as well. and we shall use error correct encoding for the binding the biometrical data. And we know that biometric identification consists of determining the identity of a person from many persons, like one to many. And biometric verification is a comparison with enrolled biometric identity. It's the comparison one-to-one. However, it's very necessary to design the biometric encrypted systems. And biometric encryption is a process that binds a pin or key to biometric so that neither key nor the biometric can be retrieved from the stored template. And here we see the example of template that is binded to key that we generated from biometrical image. In this case, we see that is an eye. However, we already speak about the face that will be used for the acquiring the biometric. And we see that some binding algorithm must be applied here. And in our case, we apply the known fuzzy commitment scheme that uses error correcting codes because of the fuzziness of biometrical template. Biometrical template is a digital reference that extracted from biometrical sample B. For template helper data, normally public open, together with error correcting codes are used. Fuzzy commitment scheme uses helper data and error correcting code to get key R, and also it uses opened helper data and biometrical features. At first, we can get the imprint or biometric features B. However, in other case, it will be covered by some noise that we say error, and we can get the B star, that is the modulo 2 summation here. And here is the system that makes the encoding and decoding of the template. We have applied a read Solomon error code because of the powerful features of this code, because it's a code that produces symbols over the Galois field, and it's non-binary code. Errors codes of length n consists of symbols that are put inside the data field, and we add the parity symbols to correct T errors in this case. For example, in this toy example, we can see that 1, 2, 3 errors could be corrected by this very short read Solomon code. And several words about the biometric noise. Fuzziness of biometric data causes noise that is defined by symbol error rate. It's the error in symbols that could appear in coding structures. FRR depends on SER of errors code and is upper bounded by this expression. And we see that the main parameter here is P, that is symbol error rate, actually defined by the biometrical noise. However, we can also evaluate the FAR when imposter produces a random syndrome during decoding for uncorrectable error. We can evaluate this value. We analyzed, in our case, the temporal smile characteristics because we know that normally smile includes 3 phases: the onset phase, apex, and offset. Here we see the diagram that has these 3 phases. And the average duration of the smile is from 0.5 to 4.0 seconds. We have applied algorithm of GÖA for sampling smile, and we got several frames to make encoding and then decoding of our biometrical template. Here is some figures that demonstrate that we have used our application to get these frames. And the structure of proposed biometrical system includes the making of smile imprint, that is a supervector from different frames, B1, etc., BM, and it's made from smile signal, actually. At the encoder block, the user password or key R is encoded with one or more ECC code words that depends on password strength and required FRR. And in verification, the use of auxiliary data, HD1, HD2 decoding C' and comparing hashes is performed here. And when hashes is equal to each other, so we give an opportunity for the user to pass. We have calculated the parameters, and here we see that parameters depend on the length of the cryptographic key and ECC applied. We found the FAR from errors for RS code 31.9 and RS code 63.15. And here we see the table with parameters, and we see that decreasing the code length improve the characteristic. The experiments were performed with staked autoencoder, and we have used the normalized grayscale images from video of size 112 by 112 pixels and scaled to 50%. Combinations of the second and third SIA layers dimensions had the values here, and we see that different values have been used for this case. And we have chosen the 63 and 31 length of the latent layer to make the encoding with the use of ECC. We have used unsupervised training of 40 users, 40 members, and we have repeated this process several times to get some statistics. And then we also applied supervised training where we added 4 additional video frames to SIA and to control the group for tuning process. Here we see the results of SIA usage, and we see that to control the intra-class and inter-class distance distributions, we have used the mean square error, and due to fine-tuning, the inter-class distribution expanded significantly relative to each other, and the decidability index increased 2.5 times. Also, we decided to demonstrate the nonlinear deformation of feature space of the autoencoder here. We see the pieces and the spots of the TSNE instrument to visualize the feature space. The example of a Reed Solomon code of the length 63.15 symbols shows that the scatter map of characters is quite huge after quantization. We see that most of characters that have values from this range are very close to 0 and Gaussian distributed. Here we see the values. And the evaluation of FFR and key size for concatenated ECC have been done with the use of quantized of real data and encoding of non-binary RS code. And there is a table that shows how the key depends on the code used, and also it shows the concatenation of the RS code of 2 lengths with linear codes. Here, the first one of the length 6, and then we shorten to 3 and 5. And we see that the FRR is improving. So the structure of the system that uses ECC is shown below, and it's seen that here is the key symbols, and they also encoded by the linear codes afterwards. And here is some check symbols here. And the conclusion of the work done includes that new biometric system based on smile imprint from face videos with the use of staked autoencoder and fuzzy commitment scheme has been proposed. Test using staked autoencoder that has 2 inner layers for 5 different groups of 40 users, and randomly selected from UVA NEMO database from 400 subjects has been done. Real data of output layer was quantized and encoded by concatenated linear and arrays codes of this length, and the redundancy was quite large, around 70%. Simulation showed that FAR values of no more than 0.5% and 1% for crypto keys of size 120 to 135 bits for biometric features dimension has been achieved. Further work can be done with other neural network structures to get more compact features and to improve the error correcting technique based on some soft decision. The work partially supported by the course action 1601. Thank you for your attention.
Thank you very much, Professor. So it was a very clear presentation, and from my point of view, so I'm very, as NCP in Horizon 2020 and Horizon Europe, I'm do happy that you are supported and participated in these cost actions, actually. That's nice. So do you have questions? I'm asking the audience in every channel, all channels we have now. If none, yes, we have none. Okay, well, thank you again, and let's continue.
Thank you for listening.
Yes, thank you. Let's continue, go to the next presentation, which will be given by Huafeng Chen, as I see. Yep.
Yeah.
Okay, formalization of people and crowd, okay, well, yeah, and crowd detection and tracking in video. You have a floor, please, dear Huafeng.
Can you see my screen? Oh.
Yes, now it's coming. I think, yes, it is okay.
Okay.
You may start.
Okay, thank you. So our title is Formalization of People and Crowd Detection and Tracking in Video. This is a joint research by Plask State University, Zhejiang University, and Belarusian State University. Well, we all know that tracking objects in video is very important in many fields. For example, for automatic driving, for security surveillance systems, but the multi-people and crowd detection is a very complex task due to many reasons, including multiple person occlusions, motion nonlinear trajectory, and the changing of illumination shadows, and sometimes objects move very fast in the frame, and sometimes the background changed dynamically, which all make the problem much more complex to solve. In our formalization, we treat the video as a sequence of digital images, and in frame, let's say FK, we have many objects, and for stationary objects, we take a set of features, the coordinates of the static object and some noise on the object. And for moving objects, we formalize the object as dynamic features of the object, the coordinates, and some noise. So we have a general rule for object detection in which we maximize the detection accuracy with some method M and some restrictions Z. For stationary objects, we use the method MSTV and the constraints ZSTV to maximize the detection accuracy. For moving object, we use another method MD and another set of restrictions ZD to maximize the detection accuracy. So basically, for person and crowd tracking problem, we can divide this problem into three types. The tracking of a single object, which we call VOT, and the tracking of multiple objects, which we call MOT, and the tracking of crowds. Tracking is to determine the location of the same object on each frame during a time interval. This will make it possible to plot the trajectory of the object, to determine its speed and acceleration, and to determine whether some action happened in the frame. So for single person tracking, the trajectory of the person, TR prime, can be found using our method MTS and some constraints ETS. For multiple person tracking, we can use MTM as the method and ZTM as the constraints. For crowd tracking, is a little different because a crowd is a large group of people with severe occlusions. It is very difficult to track individuals in the crowd, and the crowd doesn't keep the shape, the composition through time. It can split or join together with other crowds. So for this problem, we don't track individuals. We treat the crowd as an entire entity, and we use optical flow method to calculate the displacement vector. Then we build some motion maps to deeper analyze the motion of the crowd and to decide which type of behavior happened in the frame. For multiple people tracking, tracking and by detection method is most effective. If the object was detected, then with assigned with previous founded object, then we retrack, and the tracking will start if at least one object is founded. And if the object goes out of the scene, then we can save the information of the crowd for some static or variable time. But if the objects go out of the scene for a very long period, then we can delete them from the memory. The basic steps of our algorithm is to use YOLO V3 or V4 model for person detection. Then we assign some index to each person. We store information about their identity in tracklet. And the tracklet contains the following information: the current index, the image of last assigned detected result, the current object image, and the coordinates of the object on current frame and the previous frame. And we also have one visibility parameter. So our assignment is calculated based on a similarity value using Euclidean distance between current and last assigned objects. We use CNN features and some weak features, for example, horizontal and vertical shift, width and height variance relatively. Then we have to update the tracklets only for when the objects do not overlap with each other. We will update the tracklet. And for post-processing, for strong features, we used CNN features And for weak features, we use each channel from HSV color space. And for outdoor videos, we use common filter. So the important task is to determine the effectiveness of the detection and tracking stages to assess the possibility of practical use of the algorithm. For evaluation of proposed approach, we use MOT16. The experiments for outdoor and indoor video sequences was performed. For outdoor video from MOT16, the MOTA equals 0.88 for all videos from deep sort algorithm and ULOB3, and MOTA equals 0.3 for our algorithm and ULOB3 as detector. Here are some examples. You can see in the left, we use the deep sort algorithm plus ULOB3 framework, and we can see that the index is not right for the same person in the scene. But for our algorithm here, even though the person walk frequently in the room, and we still get the same index as they appear the first time in the frame. And for indoor videos, we change a little bit about the light. We turn on the light and we turn off the light. Then we turn on the light again. We can correctly identify the person in the frame, and we can record the trajectory in the frames. That is all. Thank you for your attention. I'm sorry.
Okay, yes, thank you. Thank you for your presentation. So, still, okay, so you may just answer to the question what we have in the Zoom chat. Can you open it and announce, or I may announce it by myself?
Okay.
Yep. For others, please also you may ask question orally for those who are on Zoom.
Well, I will ask a question orally if it's possible. Yes. The idea of the use of weak and strong features, what was the purpose of two kinds of features applied here? You have shown the weak features that were from the images of persons track, and the strong features from neural networks, as I have seen here. Am I right?
Let's see.
Maybe the previous slide, no? Or the slide before previous?
Previous one, I think.
Yes.
Another one.
This one? Yeah.
No, another one, second one.
Second one.
Yeah, here. Strong features that have used from CNN features. Yeah. And the weak features from H channel from HSV color space. So it seems to me that weak features were for the detection of some skin of a person, or am I right?
Well,
weak features for the detection of something, or? You have used the HSV color space, the hue, saturation, volume color space here.
Yes.
Second one. Yeah. Exactly.
Well, we use the features to calculate a visibility score. And we use the CNN features as strong features to calculate the score, but if we cannot get a very a solid result for the CAN feature. We then changed to the weak feature, which is used H channel from HS3 class space.
So it seems to me that you must switch from one features to other features. Am I right?
Yes, I think you're right.
And also the second question was according to the delay when you track somebody, then you will lose and then you have to detect once again, right?
Yes.
That's
if we lose the
delay for the tracking. So you have to update information, right?
I'm sorry.
Okay, thank you for your answers. And thank you for your talk. It was very interesting. Thank you, Mark.
Thank you very much. Thank you for your question.
Thank you for question also. So any other questions? I see none. Okay, so thank you again. Please stop sharing your screen.
Okay.
Yep, and we will proceed and go further for the next presentation. UNetX real-time pedestrian crosswalk segmentation on mobile devices. So I hope that one of these co-authors already here. Please stop sharing the screen, and so we will proceed with the next presentation. Okay, our technician will wait for a while, and then they need to do it forcefully. Please, technicians, just manage this problem. Okay, so yes, thank you. So now we can start with the next speaker. Please, the floor is yours. We can see your screen, you can start. Thank you. Unfortunately, you're muted. Please unmute yourself. You're still muted. Yep. Hello?
Now I'm sorry about that.
Okay.
So today we present you a lightweight deep neural network that segments pedestrian crosswalks on an image in real time. So there have been considerable research interests in autonomous cars in the past few years, primarily concerning the safety of autonomous vehicles. And meanwhile, every year approximately 300,000 pedestrians die on the roads, accounting for up to 26% of all deaths in road accidents, according to World Health Association. That makes pedestrian crosswalk detection an essential task to the safety of autonomous cars. So the main three approaches for crosswalk detection are based only on camera images, only on LiDAR point cloud, and on both images and point cloud. In this work, we present a convolutional neural network based entirely on camera image processing. So this network solves the detection problem as image segmentation. It partitions an image into two segments, the one that belongs to crosswalk and the one that doesn't. In this paper, we present UNetX, a 5-time more compact modification of UNet, which makes UNetX faster and more power efficient. So we took publicly available data set that actually effectively comprises three data subsets. The first subset consists of images captured by using a bumblebee camera during the day. The second one was created using the same instrument at night, and the third subset was taken with GoPro in Full HD. This set was annotated only with the crosswalk presence property. Thus, additional annotation was required. More than 3,000 of those images have been manually annotated using BGG image annotator, and its output was converted to a bitmap. The images have been evenly selected from all data subsets, and approximately 1,000 images have no crosswalk at all. Several local street images have also been added. Those images have been taken during both day and night, and also during harsh weather conditions. So, first approach was to use plain old UNet. The input is 256 by 256 pixels per image with 3 color channels. An encoder transforms all input images to a tensor 64 by 16 by 16, and the decoder with concatenation layers unpack the tensor to a single channel mask with size 256 to 200 by 256. Each value of a mask is a probability that the corresponding pixel belongs to pedestrian crosswalk on an input image. Such a network has only 1,141,000 parameters, but can we do better? So, well, we need to refer to depth-wise separable convolution. Depth-wise separable convolution is essentially 2 convolutions. The first one is a depth-wise convolution. It takes n by m by c tensor and performs c number of 2-dimensional convolutions with 2-dimensional filters on each n by m layer. The outputs of depth-wise convolution are stacked to a 3D tensor and set to a point-wise convolution. So basically, we take UNet with convolution layers and substitute all those convolutional layers with depth-wise separable convolution. And we got a 5 times smaller network with only 383,000 parameters. But as you may see on the diagram, the number of layers has been increased after such modification. So we have smaller but deeper network, and we need to evaluate its performance. In order to do that, we took the following metrics. Intersection over union is used as an evaluation metric for CNN described. It is a commonly used performance metric for image segmentation, and it measures the similarity between a predicted region and a ground truth region. The predicted region is defined by the output of a CNN with values higher than 0.5, and the ground truth is an annotation mask. The intersection over union effectively is the ratio of the area of intersection over the area of union. And binary cross entropy was used as a differentiable loss function, and is the number of pixels. So y to e is the ground truth value where the pixel number I belongs to a pedestrian crosswalk segment or not, and p of y is a predicted probability that a given pixel belongs to this segment. So both UNet and UNetX have been implemented with Keras and trained on NVIDIA Tesla V100. Each network was trained for 100 epochs. Each epoch processed the whole training set divided into batches of 32. The data set has been randomly split into validation and training sets in proportion 1/2, and after each single training epoch is concluded, the trained network model was validated against the validation set. So the procedure is quite standard, and as you may see, the UNetX takes more epochs to achieve the same metric values as plain old UNet, but eventually it gets there. So substitution of convolution layers with depth-wise separable convolution insignificantly affects segmentation results. As you may see on these examples, detected mask shapes slightly differs, but crosswalk regions are approximately the same. So again, the number of parameters decreased 5 times from approximately 2 million to less than 400,000. Intersection over union is essentially the same for both networks. It is slightly lower for UNetX, but the difference is negligible. This improved network performance on a mobile device increased by 33%, up to 35 frames per second, which is enough to perform proper real-time segmentation. Despite the dramatic decrease in computation workload, the performance improvement is modest. This is due to the almost unchanged number of loads or operations per inference and the increased number of CNN layers. To sum up, depth-wise separable convolution can be used for small networks such as UNet in order to even more decrease the number of parameters that result in slight calculation speedup and negligible impact on quality of output. Well, that's all, and I'm happy to answer your questions.
Thank you for your presentations. Please, colleagues, now the floor is yours. I mean, you may ask questions. I see none. So, just one question. What is the purpose of your topic? I mean, of this exam, of this concrete, this clear and well applied result. What is the purpose in future? How do you think?
Sorry, can you repeat the question?
I mean, what the purpose of this concrete result, of this clear result? Because actually, so it's not only for mobile device. Probably you have like pilot project or something else. What kind of the future are you assuming for this
okay.
topic exactly?
So this model can be used in autonomous vehicles for onboard computers. As a module that analyzes the exterior of a vehicle. So currently we're continuing our study and extending this to multiple class segmentation from one side, and the other side of this work is to try to make it even smaller and even more efficient to run on some embedded devices, like edge computing.
So currently you have no any pilot project to apply this result and to make like a back reaction for the car for vehicles, for example, no?
No, not currently.
Okay, thank you again, dear speaker. So now we have gaps. Yeah. We have, unfortunately, we have a gap because the next speaker will not be able to present his report. I mean, B2.5 developmental milestones of graphic technologies. So we have to go further to the sixth presentation of our section, and so this will be a presentation entitled Extraction of Human Body Parts in Image Using Convolutional Neural Networks and Attention Model. So it will be presented one of the co-authors, Viktoria Sorokina and Sergey Ablameyko. So please, the floor is yours. I think it will be Viktoria.
Yeah.
So good afternoon.
Hello.
Yeah. Okay, the floor is yours. You may open your screen and start presentation. Thank you.
Could you see my screen?
Yes.
Okay. So, good afternoon, colleagues. My name is Viktoria Sorokina, and I'm a PhD student at Tbilisi State University. Today, I would like to present the article "Extraction of Human Body Parts in image using convolutional neural networks and attention models that are written by me and my scientific advisor, Professor Dr. Sergey Ablameyko. So, what is the topic of our research? It is e-commerce. And why it is e-commerce? So what was the motivation for choosing it? As the COVID-19 pandemic reshapes our world, more consumers have begun to make their purchase online. So as a result, it causes the increase of image editing tasks, and one of them is an e-commerce catalog creation. We decided to build a system which allows generating e-commerce catalog fully automatically. So what is an e-commerce catalog? It's a set of goods and services and presented by different images of these goods. The process of creating the e-commerce clothing catalog is the following. Firstly, you need to make a full-length photography of a person, presenting several items at the same time. And after, you need to cut into pieces this photo in accordance with certain rules. For example, on this picture, you can see that we need to make a photo of this jacket. So we need to crop our model from the head till the hips. We propose the algorithm for that, and this algorithm has name smart cropping. And our main contribution was to develop the new system of image cutting in e-commerce sphere based on the deep neural network that was modified by the techniques that helps a model in training notice more important region more efficiently that it has done in the origin neural network. And to extend the existing open pose system using attention model that helped VGG architecture used in open pose to detect more image features. So the system that was developed by us is called smart cropping, and it's divided to two different stages. First is feature selection model, and the second vector and heat map building model. So on the input, we have RGB image, and then we process it by VGG18 neural network that was modified by attention model to get features from this image. And after that features was forward to open pose architecture to select the main joints of the human parts. After we calculate different relations between these points to understand the key features and to understand how we need to crop our image. And the last stage is cutting according to this rule. So on the output, we have a set of images which is represented by different type of clothes. The first stage, feature selection model, is presented by VGG18 neural network. It's a type of VGG model, consists of 19 layers, 16 convolutional layers, 3 fully connection layers, 5 max pooling, and 1 soft max layer. The main idea behind VGG is to show that classification can be improved by increasing the convolutional block and using 3x3 convolutional kernel to help highlight the features of the image. We decided to modify VGG18 by using attention model that was firstly used in NLP task and then improved to use in computer vision task. So what is attention model? Attention model is a special techniques that can be constructed into a convolutional neural block. And we have two different matrices with keys, which helps to highlight the important pieces on the photo. So what was the main changes in the architecture? Firstly, after layers 7, 10, and 18, We inserted attention estimators, on the basis of which a binary mask that is calculated where 0 represents irrelevant information and 1 is important. Then the mask represented by the matrix multiplied by the original result, and we have matrix with highlighted features, like a lot of zeros on the positions where we think that the information doesn't relate to object, and 0 where it is important. And the last fully connected layer was replaced with a fully connected layer, the input of which is the result of 3 attention estimators. Then, as a result of the previous neural network, we we forward to OpenPose, and OpenPose is an architecture that proposes 2 different branches, one branch for feature selection and one for vector generation. So we have the localization of the point, like in position 1, 1, and the confidence of the pixel that it is a necessary point. For example, left hand or so on. When we have all points of the human body, we can calculate positional relationships to understand the pose of the person. For example, we have 3-point ABC, and we could calculate the corresponding vectors that are represented on the slide. Then, using these corresponding vectors, we could measure the distance, and by the distance, we could detect the pose of the human. System right now could detect 23 key points, including head, chest, hands, legs, and even toes. So, our algorithm is capable of cropping shoulder clothes, waist clothes, hats, shoes, as well as their combination. The time needed to prepare one catalog containing 10 products is 5 minutes. We use NVIDIA T4 GPU to train our neural network. The batch size was equal to 6, and the number of iterations was 800,000. The results in accuracy is 86% for the dataset, including images of e-commerce products. I think it's everything that I need to show. Please ask your questions.
Thank you, speakers, for your clear and straight presentation. So, colleagues, you may ask questions now. I see none through all the channels we have. So thank you again. Please stop sharing your screen. And now we go to the last presentation of our current session, which will be presented one of our co-author, Vladimir Mikhailov and Vladislav Sobolevsky. So one of you have a floor, please.
Good morning.
Good morning. Yeah, we can see you.
Так, presentation. 1 minute. Так.
Yes, it's working now.
My name Vladislav Sobolevsky. Today I'm presenting a report on the topic reindeer recognition and counting system based on aerial images and convolutional neural network. Artificial neural networks are now widely used in many fields of human endeavor. One of the most actively developed area is machine vision system. Such models can now be successfully applied to solve specific application tasks. And in this report, it was decided to use them for the task of recognition and counting reindeer. Why was the decision made to develop this system? When the development began, there was only a manual method of counting the number of reindeers in the herds. In the summer, when reindeer congregate in large herds, planes would be flown over the herds and aerial photographs would be taken. The specialist would then manually process these images, counting the reindeer by head. Considering that one photo could contain up to 500 reindeer, the processing of the entire photo array took up to 6 months. In additional, the data on the number of heads was required as early as the beginning of autumn in order to make a decision about the herds. Therefore, making the decision about various conservation actions in nature reserve was not the most efficient. Before starting develop, it was first necessary to select the neural network architecture to be used in the system. The choice was made between several convolution neural network architecture. In the end, the mask RCNN was chosen. This decision was based on a number of advantages of this architecture. Firstly, this architecture was already one of the most efficient convolution neural network for object recognition by the time development began. The architecture had a number of approvals for animal recognition. These could guarantee that the MRCNN would be able to solve the task of recognition reindeer. Secondly, there have already been tests on the recognition of objects in high-density images. Since aerial photographs is done from a plane, the sound of the engines often frightens the reindeer and they huddle together in dense herds. Consequently, in most aerial photographs, the reindeer are very densely located in and often overlap each other. Therefore, MRCNN ability to handle such images was in great demand. The third important feature was that a flexible and scalable software framework had already been developed for this architecture. This allowed to the developer of the software package to begin immediately. No time had to be spent on adapting MRCNN to the task at hand. An additional advantage was that there were already developed software function for MRCNN that allowed using it for video image processing. This will allow in the future to easily adapt the developed complex for processing and analysis of aerial video images. The main training dataset for MRCNN was the Microsoft Coco dataset. This array is one of the largest dataset used to date for training machine learning models to solve detection and segmentation problems. The dataset consists of 328,000 images. In particular, this dataset contains many images of animals. However, the images of reindeer are not part of MS-COCO. Therefore, MaskRCNN by default is not able to distinguish reindeer from a number of other animals. For example, sheep, gazelles, cow, and other. Also, the MS-COCO did not contain aerial photographs, so there were many artifacts when analyzing the images. This slide shows an example of this kind of work. MRCNN recognized different irregularities or vegetation as animals. To solve this problem, MRCNN has been retrained on an additional dataset. An additional array contained 100 training aerial images and 30 test images. It may seem that a supplementary array is small, but the aerial images are extremely large. They often have a resolution of 5,000 pixels by 3,000 pixels. After retraining on an additional dataset, the trained models recognized an average of 82% of the reindeer correctly. Also, in the future, the deer recognition accuracy can be improved by retraining the MRCNN on the extended training dataset. So far, a software package with a web interface has been created for the development network, and the program itself has been deployed for limited use. The system has already been used in cooperation with the Taimirski Nature Reserve. It has also been awarded a grant from the World Wildlife Fund. Further development of the presented system is planned in the following directions. Firstly, reducing recognition errors by increasing the size of the training sample. This is especially necessary in the case of highly noisy and multi-scale aerial images. Secondly, transfer of the software complex to high-performance services. The specificity of calculation when using MRCNN imposes a number of requirements to the hardware, and the commercial use implies parallel operation and the software complex by several users. We can significantly overload the system. Thirdly, extension of functionality of the software complex by adding the ability to analyze aerial video images. Fourth, adding the possibility to use the developed complex for recognition and counting of other species of animals in aerial images. Thank you for your attention.
Thank you for your presentation. No questions? Yeah, we have no questions. Actually, I would like to ask the same question. What is currently the purpose of these algorithms? I mean, in applied life, in applied field, already is it already embedded into any complex or system?
This algorithm realized on the Python, so this may implement in other system, and now we work to implement it in system when installed on Taimyr Nature Reserve, Taimyrs, and then it be used in the program complex in offline.
Okay, do you have plan to embed it on board on the UAV? Because you have real images, so it means that if it should be in real time, it should be installed embedded into on board calculation facilities.
Yes, we think about it, but now we collaboration with Taimyr, and they have on board very specific apparature, and they know they don't have computer with the Windows system, and in their computer we cannot run our program complex. So maybe in the future we adapting our system, but at now it's we not work on this task.
Okay, thank you. So unfortunately, we have no any networking part of in this online conference. So it was just only informal meeting yesterday. We've talked about different things, but I suggest you to communicate with specialists from at least from institution. I mean, United Institute of Informatics Problems, the host of this conference, because we have at least 2 laboratories and departments which are dealing with such things, and I think we can find a synergy to communicate, to find further issues, to solve. It would be nice because you have quite similar things, quite good results, and probably it will be good for better results to communicate. Yeah, I suggest this. Okay. So, any other questions? I see none. So, we have no any further presentations. on this session. So we right on time. At least we have. Oh no, we still have time. That's good. But according to online laws, these guidelines, we will not change anything. We will be with our plan. So we will start on 2:30. So now, as we have a gap, I would like to just to draw your attention that after the lunch, after the big break, we have extraordinary, well, excellent or whatever, awesome speaker from USA. So we have a, between USA, between New York and Minsk, there is a big time gap. So he proposed to get up early at 7 o'clock and give us a speech. Ruslan Salahudinov. Actually, so he was AI research director of Apple recently, and recently he changed his job only in 2019. And what is outstanding actually, so that he was cited in Google currently for 130,000 times. So this is really big number, I should say. And so that about what we will have just after the break. Then immediately after that plenary session, we will start session A2, which will be devoted to theoretical pattern recognition problems. And then we'll have a short break, breathing break, as we're saying. And I hope we will finish before 6 p.m. because we also have 3 reports after that break. Yeah, I'm lucky that I have this hard copy program, but I'm sure that all of you already downloaded PDF from our website. Please navigate through the website, through that sections, because we have a fancy things there. We have a personality section, a web page where you can find some useful tips and useful information about our speakers, about our plenary speakers, and about speakers of the session we will have tomorrow. Tomorrow we'll have also quite outstanding session we're calling GÉANT Session, because GÉANT, it is an association for networking providers over the world. It is a pan-European network, and they try to help us to invite European projects and speakers who will tell us about their projects, about their scientific results. Among them, we will have quite big boss, actually. So he is a director of FEED Lab, which is on the top level of European Space Agency, and the lab is dealing with image processing things, dealing with Sentinel images, Earth observation, and so on. So, of course, it's connected to artificial intelligence. Yeah, also we will have a speech about EP Connect project and GÉANT as well, and other quite useful let's say, talks, which will help us to understand what is going on and currently in Europe around the artificial intelligence. I think it will be nice. As for the last day, so I'm just trying to announce what we have these days. As for the last day on Friday, on the morning, we will have a panel discussion. Also, this discussion will, the panelists are also European scientists as well as Belarusian, and one professor from Armenia, I hope we will talk about AI, information society, and the issues which is attached to the AI currently, according to legislation problems, ethic problems, as well as cybernetics issues. So I hope it will be interesting for you. So please, again, for the audience in YouTube, again, ask colleagues to subscribe and follow us, because we need to give the ability to YouTube to get our stream a little bit higher than currently it has. Yep. What else? I should remind you that all papers which were accepted to publication and to present during our conference sessions will be published electronically, and it will be published on the website according to the open license, Common Creative License BY 2.0. So this will be like, well, actually it will be a proceedings, conference proceedings. So selected papers with the further revision will be published in Springer's book. I hope the final edition of our proceedings will have around December or something like this, because they, of course, edition should go in the manner as they usually do. So now I'm finishing and trying to fill this gap what we have, and announcing a big break until 2:30. Thank you.